You may know from first-hand experience that if you open a shaken soda bottle, you run the risk of this happening: an explosion of pressurized gas and liquid. Without proper precautions, the same type of explosion can happen on a well when it first penetrates an oil or gas reservoir. That's because, similar to the shaken soda bottle, a reservoir can be highly pressurized. In it is a buildup of trapped, buoyant oil and gas in pore spaces that are being compressed by the overlying rock. When properly controlled, these high reservoir pressures are in fact advantageous. They provide the initial lift used to produce the oil and gas up out of the reservoir. The flow eventually tapers off, however, as the excess pressure in the reservoir is dissipated. Even with this fall off, natural gas will continue to rise out of the reservoir because it's less dense than even air. Oil, on the other hand, is denser than air and eventually needs to be pumped out. In either case, gas and/or oil removed from the reservoir will be replaced by water. Thus, over time, there is a nonlinear decline in the amount of oil and/or gas a well produces, accompanied by a nonlinear rise in the amount of water production. This, for example, is a plot of monthly production from a natural gas well over a 6 to 7 year period, the data being the red dots. Note how the production rates fall off exponentially. When the production curves of multiple wells drilled into a reservoir are summed over time, they lead to a production profile for an oil field that has this general shape. After the first successful wildcat well, production from the oil field rises as more and more wells are drilled into it. Eventually, there are so many wells draining the oil field that production plateaus for a period of time and then declines. Existing wells in the field continue to produce as much oil and gas as they can, but the drilling of new wells tapers off. Finally, production rates fall to such low levels that the cost of maintaining the remaining wells exceeds the value of the oil and/or gas they produce. At this point, the wells, and thus the field, are plugged and abandoned. This is an example of the history of daily production from the large J oil field in Florida. Note the rise, leveling off, and fall of oil production rates with time, as indicated by the blue line. Note also the red dashed line, which indicates the subsequent rise in water production from the field. By the last year shown in the plot, 100 to 200 barrels of water were being produced along with every barrel of oil. Finally, in the same way that the production rate curves of individual wells can be combined to produce the production rate profile of an oil and gas field, the production profiles of many fields can be combined to produce the production history for a state, a province, or even an entire country. Here, for example, is the history of U.S. monthly oil production since 1920. Note that much of the plot follows the same general rise and then decline in production seen for an oil field. However, also note the rapid rise in U.S. production since mid-2000s. This recent turnaround underscores the fact that the production history of a region, an oil field, or even a well will not always follow a simple rise and then fall in production. Production can be rejuvenated with the discoveries of new reservoirs. It can also be revived by new technologies that make previously uneconomic reservoirs of oil and gas economic to produce.